Zoom recording. Okay. So how do I do it? The whiteboard. So so remember in Cal 1, we're dealing with function with only one variable, so fx equals to y. All right, and what does it look like geometrically or in the graph? Is something like this. All right, let's say this is our function fx equals to y. Right, so at a single point, the derivative measure the slope of our tangent line passing through this point. So we use f prime x to denote what's the derivative of this function, right? So after we have the slope and the point, use the slope point formula to get the formula of the line. So that's how we interpret the geometric meaning for the derivative for a function at a single point, right? So, right, at the local minimum and local maximum, right, so this is called critical points. At this point, we have the function where the derivative is 0, right? So we find the point with derivative 0, and then we further analyze, is it a local max like this, or is it local min like this, or is neither? Is like a reflective points, something like this, right? From a concave up to concave down, right? Although it's still a critical point, but it's not min nor max, right? So this is derivative in Cal 1, and then what is the integration? Integration, we talk about the area under the curve for a function. So let's say this is A, this is B. Right. This area under the curve we call it, right, a integral from A to B under fx. Okay, and how do we compute that? We use the antiderivative. What is that? That is a function such that the derivative of the function gives you the original function fx. All right. So this is pretty much the stuff we talk about in Cal 1 that would be related, or like is analogous to the course in Cal 3 that we would be talking about. So all right, so in Cal in Cal 3, since now we are dealing with a function with more than one variable, right? So the function fxy, let's say we put it into z, right? What does the graph look like? Right. So first of all, we have a xyz coordinate system, x, y, and z. Okay, and the graph for this particular function would look like something like this. Right, it's a kind of like a two-dimensional surface, right? So imagine you have a piece of paper that have some wrinkles, some wobbling, maybe some creeps as well. All right. And on this surface, all right, let's say we pick a particular point, all right? What does the derivative on this point mean, right? All right. Or even before that, is this point even differentiable? Can we even find derivative for this one, right? So, all right, what does it mean? Does it make sense? Again, I apologize that I couldn't use the iPad to share my screen. I promise my handwriting would be much better next time. Okay, so and then how to compute that? Okay, so this is for derivative parts. And how about integration, right? Right, integration. So, and for calculus 1, we talk about integration on a particular integrals, right? That is from this the integral from a to b, right? And now we would be talking about integral for a bounded region here, right? Let's say we bounded the region here, right? So this is your area A. Okay, so we talk about we will be talking about how to integrate on this particular regions under fx and y. Okay, so as no surprise, the geometric meaning for that would be the volume, right? Suppose is under the xy plane here. So we will that integral means that we will be finding the volume under this particular surface, between this surface and the xy plane. All right, so for example, you have your piece of paper lying here, and then your flat surface xy plane is underneath it, right? You will be finding the volume between this particular cylinder type between this xy plane and the paper bounded by that region A. Right, so underneath it, this space is your region A, right? And then on top is this region on this surface. Okay. All right. And of course, we'll have much more materials other than this derivatives and integrals, but I just want to have a sort of like a big picture or general idea that what we'll be dealing with is analogous to Calc 1, right? But since we're doing with a function with multivariables, we have to have some certain basic setups, right? What does the function in 2 or 3 or even more dimensions look like, right? And what is so for high dimensions, we no longer have numbers like 1 dimensions, right? So one of the ideas is to talk about vectors. Okay. So what does vector look like, and how do we do operations on vectors, and how do we generalize straight lines, as for example straight lines in the xy plane, right? Have a slope and points, or or just 2 points that can determine the formula for the straight line. How do we generalize this idea to 3 or higher dimensions, or what is the formula for a plane in a 3-dimensional space, right? Stuff like that, and that's also very important in this course. All right, so let's go back to the syllabus. Okay, any questions so far?
Professor, this is Ray Acosta. I'm about to log in from my laptop because I was on my phone and it's about to die out. So when you see my name pop up again, just let me in.
Okay. Okay.
Okay.
Any other questions regarding the this part?
Also, will the exams be live in class, or will you upload the exams if you have a certain time to complete them?
All right, so let's jump to exam part. So the exam, we have 2 exams and the final. All right, the day would be to be announced. Probably the first exam would be in 2 to 3 weeks. All right, that covers the first 1/3 of the materials. So the exam would be administered during the class time. All right, so that I will be available during this time to answer your questions, or I will have the Zoom meeting. The Zoom meeting is will be on as usual. You can join this room, but you don't have to turn on your camera or share screens or whatever. So if you have particular questions on the exam, you can ask me in the Zoom, right? Instead of just emailing me and back and forth, that's really inefficient. And the exams will be live on the Blackboard, and then you have only the amount of time in the during this regular class time to finish the exam. So the exam time would be the same as the class time, maybe slightly more. Maybe I would have it from 3:30 to 6 p.m. Have the extra 30 minutes for you to upload your documents and etc. But pretty much after this time, you will no longer be able to access the exam on the Blackboard, right? So I want to use Lumen. Lumen is a good system, but I don't know how to set up the exam on Lumen. So I know how to set it up on Blackboard. So yeah. So the exam will be on the Blackboard, but you have to submit your exam with all your work. So basically, you have to finish your exam on the paper or on the app, but you have to write it down your whole work instead of just writing down the answer for each question. All right, and then you upload your exam to the Blackboard, and I would grade the 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 works that you submit, all right, in the Blackboard, right? Except true or false questions, I will have true or false questions. Also, I will have some short answers. Those are fine. You can just enter your answer in the Blackboard, and then I will grade it from there. But other than that, if I specify that you have to show your works, you have to write it down and then scan it and submit it to Blackboard, right? All right, any questions?
I have two questions. First question is the class gonna be, are we gonna have to prove anything, or is it just mostly computational?
And for that question, I will go over proofs for some important theorems in the book. All right.
Okay.
What is chain rule? What is differentiability? All right. But those are not very hard proof, and I'm not going to like go in depth with this. For the exam wise, I would not ask you to do any proofs.
Okay.
All of them would be computational. It shows you that you understand what's the concept and understand how you can get these concepts. Right? Does that make sense?
Yeah, no, it makes perfect sense.
Yeah.
And the second question, I mean, you'll probably talk about it later, but it's about the take-home
Mhm.
project. Like, what exactly will that like mean?
All right. So the take home I have in mind is that for each exam or each particular parts of the material, I would have a um, uh, a concept or thing that I would like you to work on, but it's like more than a homework, so it's more complicated than that. So I would make it in the take-home part. So the take-home part would have 3 questions. You choose one to answer. All right, and the whole thing counts as one exam, right? As stated in the thing, the syllabus. So the take-home, although it's only like one question, they would you have to break it down into like 2 or 3 parts, right? And then you write up your answers, your works, all right, and then you submit it to the Blackboard by the end of the semester. And then I would grade them along with your other exams, and then everything will be counted as your exam grades. Does that make sense?
Yeah, no, it makes perfect sense. And someone in the chat asked,
Yes.
if we'll be able to cover everything that's required for ODEs, Math
Oh,
255.
ODE, yes. So in ODEs, basically, you don't even need integrations. You need to know how to do partial differentiations, how to know whether or not the function is differentiable at a point, differential everywhere, or otherwise. And yeah, so know how to do derivatives is very important in ODEs. Okay, and of course you know partial different derivatives in higher orders, right? That's later on, right? But yeah. Okay. All right. So yes, putting the recordings on Blackboard. So the Zoom has the recording on the cloud. So basically all I have to do is just share the link of the recording after each class. So you should be able to access the recording afterwards. For last semester, it seems like that the recording will be expiring in 14 days, and I don't know how to deal with that if that is the issue. So uh, let me know if you want let me know if the recording says that will not be accessible after 14 days, and I would think about some alternative ways to share the recording. But so far, I will just share the link of the recording, and then yeah, you should be able to access it. Okay. So in class quizzes, I would do it probably 1 or twice in a week. It's just like a short, like 5 to 10 minutes quizzes. It's just like one question, and it covers the materials a day or 2 days before the quizzes, and also as a way of attendance. So if you were not able to do the quiz in the class, you can also do it afterwards. You see the recording, you see what's on the quiz, you submit it to the Blackboard, right? Because I will set up the submission of the quizzes on Blackboard. Everyone submit to that instead of in the class. So you can still make up your quizzes and stuff. It's not a time quiz, so but I would like dedicate 5 to 10 minutes in the class so that you can have sort of work on to that, because it's designed to be 5 to 10 minutes, and it's not designed to be an exam question. So it's sort of a way for you to like have some work on, and if you have question in the class, we can go over the quiz as well. So it's not like it's graded or like very strict, like you have to get it yourself, you have to be timed like the exam. No, it's just an in-class exercise, sort of, to it's just the same as the exams. Yes, like handwritten and then scan, or if you have iPad app, you can write it down in the iPad app, or just type it up in the computer, as long as legible and it shows your work, right? Okay. All right. So that go over the attendance as well. I'm not taking hard attendance. That the attendance is not going to be a factor in the grades, but is very highly recommended that you follows the class closely, right? Because if you miss a class, and then you didn't go to the recording to make up over it, the material next would be closely related to the material before, and then you sort of have to play the catch-up games. And since it's summer, right, we have classes back to back, and sometimes you have to catch up 2 classes at a time if you just miss one. All right, so it's not a recommended way of studying. if you stay behind and then you play catch-up games. So I highly recommend you follow the class. Even though you cannot attend the class, you can still access the recording. But attending the class has one advantage, that the recording doesn't have, is that you can ask me lively during the Zoom meeting. Right? If you feel free to interrupt and ask me questions during the class if you feel like you don't follow, or I'm talking too fast or too slow, right? Or you cannot understand the handwriting, my handwriting, then feel free to interrupt me. All right. So that's one advantage of attending the class, a live class. All right. And right, since the pandemic is still on, we have to do it in the online platform. Exams are online as well. Right, so the only way I can communicate with you is by emails or by Blackboard. So follow the Blackboard announcement, follows the Blackboard materials as well for notes. Right, I will upload the notes to the Blackboard. Right, and any other materials also follows on Blackboard. Right, the take-home parts, right, will also be available on Blackboard. I'm not going to like email everybody with that. So again, use Blackboard. Submit everything on Blackboard. Homework, quizzes, exams. Right. Right. So far so good. Okay, the makeup policy is same as the one on the before the pandemic. All right, you can, because the lowest grade, one of the lowest grade would be jobs. So usually I will not do makeups for exams unless you have a very documented excuse that I would allow you to do the makeup exam. All right. So for the grading is 90% on exams. So basically what you get average on the exam, right? Dropping one lowest exam grade, and then that counts 90% of your grade. The other 10% is from class participation and quizzes. Basically, if you didn't do well in the exams, but you attend classes and quizzes, do quizzes regularly, then you would get grades on this. Again, this is not like you don't attend class, you lose grades. This is only like only do positive effects for your grades. So yeah. So basically you get points by attending classes and do quizzes. Okay. So the homework has no grades, but homework is like extra credit for the exam. So if you do it and then you do it correctly, you get points. You get up to 5 points for the exam. So for example, if the exam, the first exam is on Thursday, and then any homework due before that count to the exam. Okay, and this is a way of because homework questions are very related to the exam questions. They are really alike. The type of questions, the materials, right? They are, so doing the homework sort of prepare you for the exams. Right. So for the answer for the homework, I feel like if I just post the answers and it sort of defeat the purpose of doing the homeworks. So what I would do is this is what the office hour for is that if you have questions or questions about my grading on your homework, you come to my office hour and then we discuss this homework questions instead of me just posting the homework answer. And also for the homework, you know that whether or not you get it right. So, but in order for you to know how you get the right answer is also very important. So I feel like this is, this part is not, you cannot get it by looking at answer or standard answer. You have to do it by doing it, and you have to do it by knowing the way the correct way to do this type of questions, right? Okay. Okay. So in terms of credit, no credit grades, the CUNY system changes regularly. So I don't know how it works in this semester. Maybe if you want to do the credit, no credit, email me about this policy, and then we can discuss this further as an option, right? For those of you who want this course to be part of your major, you have to be cautious using this option, because sometimes credit, no credit will not count this course into your major, so be cautious about that. All right. The tutoring, that's offer tutoring by the Dosiani Math Learning Center. Although they're doing it remotely because of the pandemics, I believe they're still available. All right. Look for these resources. All right. I highly recommend the tutors there. Sometimes they can help you out with the materials. Okay. So the review session, I did this before the last time I taught this course. So if enough people want to sign up for review session, I can do it via the office hour, or do it at a time outside of the class time, because the class time is really like tight, and there's no room for doing a review session, right? But if ever enough people sign up for it, and they are willing to do it at a specific time, and then I would more than happy to have a review session, right? Talking about quizzes, homeworks, right, and stuff like that. Right. And also it's very important for you to have some connections with classmates, right? Someone asked to set up a Discord. I highly recommend doing that, all right? Because you engage with other people, so that you have better understanding of the materials. You can even do homeworks together, quizzes together. Just don't do exams together, right? But yeah, you collaborate. That's how you learn, right? How many questions will each exam roughly have? For last time I taught it, but it's like 5 to 8 true or false questions, and some short answers, But for the long questions, I will have maybe 2 to 3 long questions that you have to write your work on. Again, this exam is designed for you to, complete it within 2 hours. So it should, it shouldn't be, very a very long exam, but I would try to make these exam covers as much materials as possible. Right? Does that make sense? Okay. All right, so that covers everything on the syllabus. Is there any other questions for the syllabus? All right. So the first thing we want to do in this class, the very beginning of the class, is to talk about what is vectors. So a vector is an analogy to numbers, right? So if we have real numbers, right, and then this is only covers one dimensions, right? You have only information in one dimension, and if you want to have information for 2 or 3 or more dimensions, you have to use vector instead. All right. So a vector is just a so, and let's be more precise, an nth dimension vector is a n tuple. So you have a1, a2, all the way to an, right? Such that each a1, a2, an is a real number. And this represents a vector in Rn because it has information for in the first dimension, second dimension, all the way to the nth dimension. So it has information for all dimensions, right? And what does it look like really in geometrically? So a vector in this case is x, y, z. So a vector is a pointed arrow from the origin to this point x, y, z. All right, and this pointed arrow has two information stored, right? It tells you the direction and also tells you the length. All right. So a vector may have the same direction as this vector, but has a different length. So if we just elongate this vector, this arrow longer, right? It still lies in the same direction, but it has a different length. Or sometimes is you push this arrow backwards, right? It points it to the opposite direction. Okay, and this this will no longer be the same vector as the original vector, but it shares one information, that is the direction, right? It points the same direction or the opposite direction. Basically, in the same line, right? These vectors lie in the same line, right? A vector may also have the same length with this one, but not pointing in the same direction, right? So if we draw a circle around the origin with this length, right? Then every vectors on this circle will have the same length, right? That's the definition of a circle. But as you can see, they point in different directions. All right. So these two information are important, as distinguishing vectors. Also, very important for extracting from this vector, because we need the direction to determine the line passing this vector. All right. Also, we need sometimes we need the length to do orthogonal projection. Right. Those are later on. Okay. So, what are the operations on vectors? All right. So if you have vector 1, v1, that is x1, x2, xn, and you also have v2, in this case is y1, y2, yn. Right, what does it mean to add this vector? All right, so in a geometric interpretation, right? If you have v1 here, let's say you have v2 here, right? The vector as a result of this addition of these two vectors is precisely the vector on the diagonal of the parallelogram with these two vectors as an edge. Right? So is this one, okay? 1 plus, right? To see what why is this diagonal vector the sum of this vector, you can think of, because it's a parallelogram, right? These two edges are parallel to each other, right? Although I'm not drawing like it should be, right? So these two are parallel. That means they point in the same direction, and they also have the same length, right? The only difference is that this start at the origin, but this does not, okay? And since you translate this to here, right? V1 plus V2 means that you go from the origin to the point here, and then you go from here to this point by going along this vector V1. So you can think of it as you add V2, right, goes to this point, and then you add V1 afterwards to get to this point. Right? But as you can see that the addition is commutative, means that you can switch the order. Why? Because you can also go from V1 first to this point, and then go along V2, the vector V2, to get to the same point. So the end result is from the origin to the endpoint here. So that is the resultant vector, okay? So this is the geometric interpretation that the sum of the vector is the diagonal vector of the parallelogram formed by these two vectors. Okay. In terms of the computation wise, is pretty straightforward. All right. So if V1 again is V1 is equals to x1, x2, and 2 is y1, 2. Okay, then V1 plus V2, no surprise, is just adding the number in each dimension. So x1 plus y1 goes to the first dimension, x2 plus y2 goes to the second dimension, all the way to xn plus yn. Right. So as you can see, why this is commutative, because if we switch the order, v2 plus v1, you're just adding each dimension in the fashion as y1 plus x1, y2 plus x2, yn plus xn. But as you can see, that addition is also commutative, right? x1 plus y1 is the same as y1 plus x1. Same thing for here, all the way to the n dimensions. Okay. So that is the addition on vector. And also, what is, if you have addition, you may also have subtraction, right? Subtraction, on the other hand, is not commutative. So that means V1 minus V2 is going to be different than V2 minus V1. Okay, you can think of it as because you're going from to V1, right? So imagine you're going along V1 from the origin, okay? And then minus V2, that means you go the opposite way of the V2. So instead of going here, you're going the other way. So you go from here, go the other way, right? But when you translate this part, right, as not starting from the origin, let's say this time you start at the point ending at the end of the vector v2, right? So now you go first you go opposite of the direction of v2, so you go back to the origin, right? Because it's the opposite direction with the same length, right? And now you go along the vector v1, so you end up with the point at the end of the vector v1. So the vector you are looking for is the vector joining these 2 points. All right, because you start from here and then you end with here, so the direction is going this way. Okay, so this is v1 minus v2. Okay, you know, similarly, if you want the other direction, right, let's say v2 minus v1, now you go from the point ending at the end of the v1, and then you go to the point at the end of v2, and this is your vector v2 minus v1. Okay, to sum up that the subtraction of vectors means that you you get the result as the vector joining the endpoints of these 2 vectors. All right.
Professor, so the black line represents the endpoint of V2 down to the endpoint of V1.
Which one? Which line?
The black line?
The black line, yes.
So
You start from the
So
endpoint
that-
of V2, you go to the endpoint of V1, right?
Okay, and then the blue line is the endpoint of V1, the endpoint of V2.
V2, yes.
Okay, just want to make sure.
Yeah, so to see that, you know, you can just follow the way, you know, before minus V1, you go you know, to the opposite of V1, you go back to origin, and then since you're adding V2, you go along V2, so that's why you are ending up here. You start from here, you end up here, right? Same thing for the black line, right? You go opposite of V2, you know, from this to the origin, and then you go along V1. That's why you end up with the point here. Right? Start from here, end up here. All right. So let's do some examples. So let's say if you have V1 equals to 2 minus 1, 3. V2 is 4, 2, 1. So V1 plus V2 is equals to 2 plus 4 minus 1 plus 2, and then 3 plus 1, which is 6, 1, 4. And V1 minus V2 is equals to 2 minus 4 minus 1 minus 2, and then 3 minus 1. And in this case is minus 2, minus 3, and 2. You can verify your answers by plugging into the graph. Right? You will see that the vector on the diagonal would be the same as 6, 1, 4. and then this represents the vector from the endpoint of V2 to the endpoint of V1. Right, we have the same vector as -2, -3, and 2. Okay. Right. So since we're talking about vectors,
Professor, can you go back to that last screen before you so I can copy it down?
which one?
The last numbers you had up, the example. Yeah, that right there. Just give me 10 seconds.
No problem. No problem. Make the font larger. Okay. Let me see. I can do it.
Okay, I'm good.
Okay. How do I do that? Like this. Right. Is it better?
Hi, Professor. I had a question.
Yes. I couldn't hear you.
Oh, hi. I just wanted to know if there was a way to graph this.
You can always graph vectors in 3 dimensions as long as you know how to graph the xy plane.
Okay.
Right. So for example, a V1. For example, this is your XYZ plane. So you have 2 in the x direction. So 2 at the x direction, -1 at the y direction. So -1 here. And 3 at the z direction. So 3 here. So basically you draw parallel line, parallel line to the x-axis, y-axis, and z-axis, so that you lined up your intersections at -1, 2. So this is your point that matches your x and y. And then finally, you draw a parallel line to the z-axis, so that you parallel to the one that the z value is 3. So that would be your vector v1.
Okay.
Okay. So similarly to similar to doing vectors at xy plane, right? You first find out what's your x value, right? And then you draw a line parallel to the y-axis. Then you find your y value, and then you draw a line parallel to the x-axis. The intersection would be the point you're looking for that matches your x value and y value, right? For higher dimension would be a little bit more complicated, because you have to match up your x value, right, 2 here, your y value -1 here, and also your z value. So after you match your x and y, then you can have a parallel line passing through this point to the z-axis, right? This one would be parallel to the z-axis, and then you find the z value of 3 so that it has a parallel line to the z equals to 3. Does that make sense?
Yeah, it makes sense. I'm following.
All right. Okay. So this is your V1, and then I assume the V2 would look something like this. Right, this is rough drawing. Then this is the parallelogram in the XYZ plane, so that the diagonal vector would be here. V2, right? And then V1 minus V2 is the one that goes from the endpoint of V2 to the endpoint of V1. So this vector, the red vector, would be V1 minus V2.
Okay.
Right. As you can see that this vector is also a diagonal vector of this parallelogram. Right. It's the other one. There are two diagonal vectors. Okay. And similarly, if we want V2 minus V1, you just switch the endpoint. So now in this case, you go from the V1 to V2.
Okay, thank you.
All right. Okay. So for vectors, every vector, actually vector space would have a standard basis. Again, if you have, took the course of matrix algebra or linear algebra, a basis would be more general than the basis that we're talking about in R3, right? Or in general Rn, right? Euclidean spaces. So for the standard basis, we only talk about standard basis in n dimension Euclidean spaces. That is the space Rn represented by n-dimensional vectors, right? So the standard basis, as you can imagine, is the basis that only has information at one dimensions. So it would be 0 everywhere except in the ith dimension. And then 0 everywhere else. Okay, so the important idea of this basis is that you can represent every vector by a linear combination of the standard basis. All right, so for example, if you have V1 is x1, x2, xn, right? It's just x1 times your vector ei plus let's do it, break it down. x1 times e1 plus ex2 plus e2 dot, dot, and en, right? One important thing to notice is that this x1, x2, xn, they are all numbers, and the e1, e2, and en, they are vectors. Basically, you're adding vectors together, right? So why do we need to do that? Is that for each vector v1, v2, right? They are different vectors, but they are but if we use the standard basis, right, you can represent it by the same set of bases, right? The standard basis, and then the standard basis would be important to tell you the information specific to that dimensions. All right. So in oh, by the way, is everyone okay with this part?
Professor, I'm kind of, what does the standard basis, like what does the EI, what does that represent?
Which one?
Like EI, E subscript I?
Yeah. So this is the standard basis specific to the I dimension. So the set of all standard bases consists of all the EIs. Right. I is from 1 to n. Sorry, let's do that again. Right. So in n-dimensional Euclidean space, you have exactly n numbers of standard bases, right? You have E1, E2, all the way to En, right? So what does E1 look like? E1 is just 1 at the first dimension and then 0 everywhere else.
Oh, okay. So it's just, okay. So this is like making just a field of vectors, essentially.
Yes, yes,
Okay,
yes.
yeah, all right.
Right.
Makes sense.
So the advantage of using standard basis is that you have a general representation, right? You use a set of vectors to represent all vectors in the space Rn. Right? As you can see, every vector is a sum of vectors in Rn. Right. Right. Actually, before, by the way, everyone good with this part?
Yeah.
Okay.
Yeah.
Okay, so before that, actually, I forgot to mention that for operation on vectors, you also have scalar multiplication. Right. So this is when you apply a scalar, a number, to a vector v1. So let's say your v1, as usual, is x1 dot dot xn. If you apply a scalar to it, that means you apply the scalar to each dimension. and then this forms the new vector. Right? Geometrically, what it means is that you keep the direction of v1, but you change the length of v1 if it's positive, or sometimes if it's negative, you even change it to the opposite direction. But the important part is they point in the same direction or the exact opposite. Right? Basically, the new vector will have the same would stay at the same line as the original vector. This is the same line that all these vectors are lying. So this is the line that pass v1, right? Every scalar multiplication of the vector v1 would also lie in the same line here. Maybe the same direction or maybe the exact opposite. Okay.
Professor, I have a question.
Yes.
So where it says A times V subscript 1, is that A1 there or is that just a comma?
Oh, I'm sorry. It should not be a A1. So yes, only A here. This is the
Starting route to 3444 Grace Avenue.
I'm
And
sorry.
northeast on Adam Boulevard.
Okay. All right. So far, so good.
Yes, thank you.
Okay. So as you can see, the standard basis. Okay. Right. Right. I is just the vector with the length 1 at the x-axis. The j. Actually, I'll use E1 to avoid confusions. E2. E2. This is E1. And finally, you have E3. All right, because these three standard bases only tells you information in one dimension specifically. So E1 has points at the same direction as the x-axis. That's the information on the x value. E2 is at the y-axis and E3 at the z-axis. And also very important is the length, right? Because you only have one at that dimension. That means the length here is 1. Same thing for E1, right? The length is 1, E2 also 1. Right? So as you can see that the any vector, let's say V1, you elongate the E1 by scalar multiplication. So here, X EI, E1, X1 E1. And then you elongate or put it the opposite of E2. Right? This is your X2 E2. And finally for E3, right, this is your X3 E3. And now you add these three vectors together, right? These two vectors together gives you the diagonal vector. Again, now you add this and the X3 E3. Now you have the diagonal vector with this parallelogram. Does that make sense? All right. As you can see, you can do it in more than one order. You can add x and y first, and then add this diagonal to z, like I did here. Also, you can do it, using different orders. You can do it as let's say y and z first. Get this vector, and then now you add this. Vector with the x vector. The result would be this diagonal vector in this parallelogram, right? And the result should be the same, right? So that tells us another information about vector addition is that vector additions is associative. So the order of adding vectors doesn't make any difference. So to write it down, you have V2 plus V3 is the same as you add V2 and V3 first, and then you add them back to V1. Before you add the first two first, and then you add the results as into the V3, the same as you add the last two together first, and then you add them to the first vector. Okay. All right. Everyone so far so good? Can I move on? Okay. So in R3, the standard basis has a specific name. So your E1, which is the one that only takes information at the x-axis, is called the I vector. E2, which is 0, 1, 0, is just J. 3, 1 is just K. So it's just in the notation clarification that if you see I and J and K as vectors, that means that we're talking about standard basis in R3. Okay. Right. So if we represent vectors in R3 with I and J and K, right, and this representation is unique. Okay, so you cannot have a vector with two different representation with the same basis. So as you can understand, if you have x and y and z as a vector in R3, right? This x tells you the information in the ith vector. So this is, what do you call it? This one you cannot change it, with the different axes, right? Same thing for j, right? If you have y value in the j dimension, this y is also unique. The other y doesn't do it. Right? Same thing for the k. Right? So this combination is unique. If you change x, let's say to x0, even though you keep the other two the same, these two are different because you changed the information in the x-axis, right? And how about if you change it to x0, y0, z0, somehow they lined up. You couldn't do it because let's look at the difference, right? Right. Remember the subtraction of vector tells you about the vector joining these two endpoints. Okay. So you have x minus x0, I and z minus z0. Okay. In order for two vectors to match up perfectly, right? These two vectors has, if they want to be the same vector, that means the endpoint must agree, right? Because they all start with from the origin. So if the endpoint are the same, that means you go from the same endpoint to the same endpoint. That means this vector must be 0. But the only way to make this 0 is for this to be 0 this to be 0 and also this to be 0. Right? Because if you add I and j, you will never get 0. If somehow they are they have non-zero values, right? Because these two are perpendicular to each other. So any parallelogram you draw, right, they will have a non-zero vector from the origin that gets you non-zero. So the only way to get 0 is to have 0 at each coefficient. So that means that x and x0 are the same. Y and y0 are the same. Z and z0 are the same. So that's the power of standard basis is that the representation is unique. If you have another representation that shows that represent the same vector, this two representation has to be the same. Does that make sense? Okay, so the last material I want to cover is the in let's say R. So this would be analogous to the idea in XY plane. So call that in XY plane, if we want to have the line, the straight line formula, you have different ways to do that, to obtain that. The one is called point slope, Okay, so what it means is that we tells you what the slope of the line is, right? That tells you the shape of the line, right? It may be going tilt up or going down, how steep the hill is, right? And then tells you what point this line pass, and that's enough information to show you. So this is the point P, and then the slope here. Okay. And this two information is enough to tell you the for you to obtain the formula for the line in XY plane. How do we generalize it to the n-dimensional space? Because you run into problem right away is that slope doesn't make sense in n-dimensional space. So for example, in XYZ plane, what does slope even mean, right? We know you want to show you the the slope shows you the shape of the line, but the shape of the line, this this line and this line doesn't look much different, because if we just rotate it, right? If we just rotate this line, you look at it at a different angle, it shifts to this to here. So it doesn't really make sense. All right. And also, when you talk about slope, does it regard to the XY plane or the YZ plane or XZ plane? Because you have more than one plane than the XY plane you talk about in 2 dimensions. So let's see. So instead, we talk about we use the formula with a point and vector. Remember, for a vector, it has information as the direction. So we use that information to represent the line, right? Because each line, if we shift the line that only pass the origin, so let's say this is the line we want to interpret, and then we shift it to here so that it passes past the origin. Keep it parallel because we want to keep the direction information consistent. Okay, and you can have a vector here so that this vector is on this line. So this vector tells you the information about the line. I mean the point in every point in this line. Okay, so for example, if your V is X, Y, Let's not use it twice. 1, 2, 3. So every point in this line, a red line here, is just a factor of v, the vector v. So let's use TV such that t is any number from the real line, any real number, represents this straight line. So this is a one-to-one correspondence. Does everybody clear? All right, but we want to translate this line to the one that we actually want to interpret, right? Because we remember we translate this line so that it pass the origin. Okay, so because it has to pass P, so what is the solution is that, let's say the red point here is t something t, some t times your vector v, right? We want to translate this point to the actual line. So what do? Is that we just add the vector p. Okay, so that yes, give me a second. So that the end result would be a point corresponding to a point at the actual line here, right? So you can see that because you can see that from the parallelogram here. It's a little bit difficult to draw the parallelogram. Right? So by adding the vector p, we match the point at the red line to a point at the actual line that we try to interpret. And we just do it for every point at this red line so that we will get every point at the actual line. So that's how we can obtain a formula in the straight line in n-dimensional vector space. First, we know, if we know the vector that is parallel to this line, right? In this case, we pick a vector v, right? And then we use v, right? We span it so that we can get a straight line that pass the vector v. We span it so that we not only get a vector, we get a whole line, right? And then from this straight line, because we are only obtaining the parallel line, right? The actual line has to pass a point P. So the solution is that we translate the point here to the actual line by adding the vector P. Okay. So for example, your point P has a coordinate x0, y0, z0. So the points at the points at this line pass through P and parallel to the vector V would be what is TV is TV1, TV2, TV3. So TV1. TV2, TV3. And remember, we have to add the vector P, right? The vector P x0, y0, z0. So we have to add v0, the x0 to TV1, y0 to TV2, and z0 to TV3. And in this case, T is any real numbers. All right. So for example, by the way, any questions before I move on?
So in essence, you're basically creating a plane between those two vectors, and the red vector is a vector you constructed with some magnitude t0. And would it be right in saying, like, I guess, like, analytically, how would this, like, I guess, result? Like, are you like taking the integral of all those additions of those vectors from, like, is that what that means? Or because I'm trying to...
It's not integrals, and I'm not creating any planes. All I do is I translate the line. The black line is the one I want to have a formula, or I try to interpret, right? So I translate this line to the red line because I wanted to pass the origin, right? Because I know it's parallel to the vector v, that means the vector v has to be on the this straight line. So in this case, your v is somewhere. Use purple. Your v is here. Let's say v is here.
Oh, so we're just simply translating from...
Yes.
Okay.
Yeah, because we know the information about v, right? So the information of this red line is just spanning the vector v. What do I mean by spanning? Because is that we just put out every possible scalar onto this V. Right? We
Okay,
stretch
yeah.
it as many as many magnitude as we want, so that it covers every point in the straight line. Right? The V is here, it covers only one point. But if we stretch it for any any real numbers, it will get to every point in the straight line. Does that make sense?
Yeah.
Yes. So now we have information of this red line, but how do we get from the red line back to the black line is by adding the vector P from here, and then we go back here by this parallelogram. Does that make sense? Every time we add it, you translate the T0V to actual point in the back line, so that we do it for every T0, right? That's how we get from TV to TV plus P. So the end result is that this is a formula, or this is one way to represent the points in this black line. Right. So for example, can I do an actual the actual example? Move on. Okay. So let's say in this case you have V. So 2, 3, and minus 1. And then your P has to pass, the point you have to pass is 1, minus 1, 0. So you have to the red line, actually, let me phrase that. The red line, right, the TV that we just talked about, all vectors with the form 2t, 3t, and then minus t, such that t is t a real number. But how do we get from the red line to black line is that you have to add the vector P at every span of V. So, which is TP plus V, a P. It's just every vector you add 2t, 3t, and minus t with your actual vector P, 1, minus 1, and 0. Again, P is real numbers. But what is really the addition look like, right? We simplified it, so it's just 2t and 1, you plus it together. 3t minus 1, and then minus t plus 0, which is minus t. So this is a representation for the line parallel to the vector v and pass the vector p. Right. So for example, when t is let's say when t is -2, when you plug it in, you get a vector -2 times 2, which is -4, plus 1 is -3. -6 minus 1 is -7, and then 2, right? So you get this point. That means that this point is in the line. Right? Vice versa, if you want to see if a point is in the line, let's check if, let's say, I don't know, 4, 2, 1 is in the line. the only way to for this point to be in the line is that you can find a specific t such that this vector is exactly equals to 4, 2, 1. So you want to find a t such that 2t plus 1 is equal to 4, 3t minus 1 is equal to 2, and then minus t is equal to 1, right? These three equation has to hold simultaneously, right? So if you solve the third equation, you solve it right away, right? T is equal to 1. So when you plug in t equals to 1 here, 3 minus 1 is 2. That's good. Right. The second equation also tells you t. Wait. Hold on a second. So the third equation tells you t is equal to minus 1. The second equation tells you t is equal to positive 1. And the first equation tells you t has to equal to 3 over 2. As you can see that you cannot have one t that satisfies all three equations. So that tells you that there's no t. There's no such t. Right? That means that it's not in the line. So that's the power of this formula for the line, is that you can check whether the point is in the line. Also can tells you to find specific points in the line. Okay. So this 4, 2, 1 is not in the line, but let's say if we want minus 1 and change 4 to 3. Let's say 3, 2 minus 1. Right. This would be in this case this point would be in the line. As you can see that we change. This is 3, and in this case 1 minus 1. So third equation tells you that t has to be equal to 1. And also the first equation also tells you that the t has to be equal to 1. Okay. So all three equations tells you t equals to 1. That means that t equals to 1 is the perfect t we want that satisfy all three equations. So if there is such t, that means that the point is in line. So in this case, there is such t, so it's indeed in line. Does that make sense?
Yes.
Okay. Good. All right. The last thing is that the second way of doing this the line formula is that sometimes you don't have the vector. You only have 2 points. You only have 2 points in the line, let's say P1 and P2. Right? But we know that the how do we get a vector, right, joining 2 points? That's the subtraction of vectors, right? So we can have a point vector formula right away just by subtracting these 2 vectors. Now you have a vector v, and you also have a point. So you go back to the vector point formula, except in this case, your v is P2 minus P1, which is, let's say P1 is X1, 1, C1. P2 is X2, 2, Z2. So now your vector would be P2 minus P1. So is X2 minus X1, Y2 minus Y1, Z2 minus Z1. Right. Now you have a vector. You can pick any point, right? P1 or P2, any point as you want. Let's say I pick P1. So your the formula for this point would be TV plus P1, which is the V is X2 minus X1 times T. So X2 minus X1 times T. Right, don't forget to add your P1. P1 is X1, Y1, Z1. So plus X1. Right, that's the X coordinate. Y2 minus Y1, T plus Y1. That's your Y coordinate. And finally, Z2 minus Z1, T plus Z1. Okay. Any questions so far? So that's everything I want to cover for this class. All right.
I don't have any questions.
Yes.
Oh, sorry.
Go ahead. Who asked you? Who asked it first? Go ahead.
Can you go over the TV part again? Because I don't understand the handwriting.
You mean this part? Wait, hold on a second.
The last part, is that TV plus B1? Yeah, right there. Is
right
that
here?
TV plus B1? Yeah.
Yeah, TV plus. So remember, for the first formula, you have if we know the point and a vector parallel to this line, right? this is the formula we have. We have t, we span the vector by a number t. T is anything. Right? T is any number in the real line, any real number. You span the vector v because you have to pass a specific point. So we have to add the point so that you go back from the red line to the black line. Remember?
Yes.
Okay, so same idea here. We have a vector. We construct a vector that is parallel to this line. Right? This is the vector joining these 2 points via the subtraction. So now we have the vector, and then we pick P1 as the point we want to pass, right? So now we have to span the vector V first, and then you have to add the vector P1 so that it goes back to the black line we want to interpret, right? So what is your V? V is P2 minus P1 is x2 minus x1, y2 minus y1, z2 minus z1. So t times v, right? We span the vector v is you apply t to the x coordinate x2 minus x1, t times y2 minus y1, t times z2 minus z1. So this is your tv. Let's put tv here. This is the tv part. Okay, but we also have to add your P1. So that's why you have to add x1 to here, y1 to the y coordinate, and the z1 to the z coordinate. That's the complete formula, you know, if we only know 2 points.
And you would still do the same idea from before. You would find a t such that it fits that line, right?
Yeah, find a t such that fit, right. So if we want to check, so if we want to find a point, point in the line, right? So it's the same as finding such t that satisfy, you know, equation 1 right, for the x coordinate, equation 2 for the y coordinate, and equation 3 for the z coordinate. Okay. Because again, the t here is a spanning coefficient. Right? Any t, we want to span the line. That's why we want to pick any real numbers. So t represents any real numbers. All possible real numbers. Okay. So far, so good.
Yep.
All right. It's 5:30. I want to end the class. The recording will be soon by tonight, and tomorrow we will be covering. So next time we will talk about inner products, right? Which is a dot product. This is the only inner product we want to talk about. In the Rn, and then do and related things about inner products like orthogonal projection. That's all a very important thing to talk about. So Cauchy-Schwarz inner products, orthogonal projections, and distance from a point to a line, or distance from a point to a plane. Okay. All right. So see you guys tomorrow. Right.
All right. Thank you, Professor.
Bye bye.
Thank you.